100 times the speed of light. That is the number Hendrik Lorentz calculated in 1925 and then quietly delivered to two physicists who had just published a paper proposing that electrons physically spin. If the electron surface carried enough angular momentum to match what experiments were measuring, that surface would have to move at roughly 100 times the velocity that light travels in a vacuum. Some estimates put it higher. None put it within reach of any speed the universe permits. The two physicists, George Oland Beck and Samuel Goldam, immediately went to their supervisor and asked him to withdraw the paper before it reached readers. He told them it was already in print. He also told them that being young was an advantage. Young physicists could say foolish things without permanently damaging their reputations. The paper was not foolish. The measurement it described was correct. The quantity it named was real, observable, and consequential. It would eventually explain the structure of every atom on the periodic table, the hardness of every solid surface you have ever pressed your hand against, and the operation of every MRI machine in every hospital on Earth. What was wrong was only one thing. The picture behind the proposal, the electron, is not spinning. Nothing with the electron's size and mass could carry that much angular momentum through physical rotation without requiring a surface speed that makes the whole calculation physically impossible. And yet the quantity is there. In every atom of your body right now, electrons are carrying something that behaves exactly like angular momentum. It deflects in a magnetic field the way angular momentum deflects. It adds to orbital angular momentum in exactly the right proportions. It comes in a fixed amount that cannot be increased or decreased by any force or process known to physics. It is conserved with the same stubbornness as any other angular momentum in the universe. It determines the color of every element when heated, the capacity of every electron shell in every atom. And the reason matter holds its shape instead of collapsing. It is not rotation. The name that attached itself to this quantity was spin, a name chosen before anyone understood what it was, retained afterward because no better word existed for something the language had never needed to describe. Every electron, every proton, every quark carries spin. Every photon carries spin. The universe describes all of them as rotating. Not one of them is. What spin actually is beneath the borrowed word and the misleading image of a tiny ball turning on an axis is a relationship. A relationship between a particle and the geometry of the universe it inhabits is written into the particle at a level so deep that removing it would not leave a simpler particle. It would leave something that is not that particle at all. That is what this exploration is about. The place to start is not with electrons, but with the ordinary classical version of angular momentum, the kind you can see in a figure skater pulling her arms in mid-spin and feeling in a bicycle wheel resisting the tilt of a turn. Before you can understand what quantum spin is, you need to understand what classical spinning actually gives you, and why that framework breaks completely at the scale of the atom. What does spinning actually give you? Think about a gymnast in the middle of a backflip. She is pushed off the ground, and she is airborne, rotating backward. Now, mid-flip, she pulls her arms tight against her body and draws her knees toward her chest. The rotation accelerates, not because she pushed harder, not because new force entered the system, but because she redistributed her mass closer to the axis of rotation. This is angular momentum conservation in action. The total angular momentum of the gymnast stays constant the moment she leaves the ground, and nothing outside touches her. What changes is how that angular momentum is distributed. When her arms and legs are extended, the mass is far from the axis, and the rotation is slower. When she tucks, the mass moves inward, and the rotation speeds up to compensate. Same total, different configuration. Angular momentum is one of the most precisely conserved quantities in the universe. Along with energy and linear momentum, it makes up the set of quantities that nature tracks obsessively and never allows to disappear. You can move angular momentum from one object to another. You can change where in a system it resides, but you cannot create it from nothing, and you cannot destroy what exists. Angular momentum is not the same as speed of rotation. It depends on three things together: how much mass is involved, how fast that mass is moving, and how far that mass is from the center of rotation. A large, slow, massive object spinning at a great radius can carry enormous angular momentum. A tiny, fast object spinning very close to its center can carry very little. The gymnast tucking mid-flip is trading one configuration for another, while the total stays locked. It also has a direction. The direction of angular momentum runs along the axis of rotation like a flagpole through the center of a spinning wheel. When the gymnast rotates backward, her angular momentum points horizontally in a specific direction relative to the room, perpendicular to the plane of her body's rotation. When she lands and stops rotating, that angular momentum transfers through her feet into the floor. Conservation is always exact, and it is always local. The angular momentum did not vanish. It spread. What matters for what comes next is this. In the ordinary world, angular momentum is continuous. The gymnast can have any amount of it. She can spin fast or slow. She can carry 10 units or 10,000 units or any value in between. There is no forbidden gap, no step that cannot be made smaller. If you want slightly less angular momentum, you make a slightly smaller adjustment to your configuration. The quantity slides along a continuous scale. The way a volume dial turns smoothly from silence to full without jumping between fixed steps. This is the picture that physicists carried into the early 20th century when they began trying to model the atom. They assumed that electrons moving around the nucleus could carry any amount of angular momentum. You want an electron with a bit more? Fine. Nudge it into a slightly larger orbit at a slightly higher speed. The angular momentum adjusts continuously the way the gymnast adjusts her spin. That assumption turned out to be wrong. And the experiment that broke it did not arrive from a theory. It came from a simple observation about light that had been sitting in plain view for 50 years. When you heat an element to a high enough temperature, it glows, but it does not glow with every color. It glows at specific, precise colors, and only those. Hydrogen has 4 visible lines. Sodium has 2. Every element has its own signature as unique as a fingerprint, as narrow as a single ruled line in a notebook. Burn hydrogen anywhere in the universe, and those same 4 lines appear. This had been known since the mid-19th century. What nobody understood was why. Why not every color? Why these exact colors and no others with nothing between? The answer, when it came, would demolish the continuous picture entirely. It would come from a man staring at those spectral lines and asking what kind of orbits could possibly produce them. Imagine you could tune a radio that could only receive certain stations with nothing but silence between them. You spin the dial, and at one point you get a signal. Spin further, and silence. A bit further, another signal, more silence. Further still, a third. And nowhere between those points does any signal exist. No matter how carefully you tune, no matter how slowly you move the dial, the silence between stations is absolute. The stations are discrete. The space between them is empty. The atoms of every element are exactly like that radio. They emit light at fixed, precise frequencies and nothing between them. The discrete nature of those frequencies was the first crack in the classical picture of the atom. The crack that Niels Bohr turned into a theory in 1913. Bohr was a young Danish physicist working in Manchester in the aftermath of Rutherford's discovery that atoms have dense, tiny nuclei. He had the same picture everyone else had. Electrons orbiting the nucleus, the way planets orbit the sun. The orbital mechanics were classical. The electron moves in a circle attracted inward by the positive nucleus. Its centripetal acceleration is balanced by its orbital speed. This all made sense except for the spectral lines. In classical physics, an orbiting electron is in an accelerating charge. An accelerating charge radiates energy. If an electron is continuously radiating energy, it loses speed and its orbit shrinks. Within a fraction of a second, it spirals into the nucleus. Classical physics predicted that atoms would be instantly unstable. They are not. Something was protecting the electrons. Something was keeping them in place at specific distances from the nucleus. Something was making certain orbits stable and forbidding every orbit in between. Bohr proposed something radical. He declared that electrons could only occupy certain specific orbits, and in those orbits they did not radiate. He offered no derivation from any deeper principle. They simply existed stable until something kicked them into a different orbit. When an electron jumped from a higher orbit to a lower one, it released the energy difference as a photon of light. The color of that photon corresponded exactly to the energy gap between the two orbits. The spectral lines were not random. They were a map of the allowed energy gaps in the atom. The discrete colors of hydrogen light with a fingerprint of hydrogen's specific allowed orbits. And here is where angular momentum entered the picture. Bohr's allowed orbits were not arbitrary. He showed that each stable orbit had a specific angular momentum, and that angular momentum was always a whole number multiple of a fundamental unit. That unit is called the reduced Planck constant, abbreviated as h-bar in physics. It is an extraordinarily small number, about 1.055, 10 in teens, of 34 kQi, or the 2 m squared e's. Vanishingly small by any everyday standard. But at the scale of electrons, it is everything. In Bohr's model, the electron in the first allowed orbit carries exactly 1 unit of h-bar of angular momentum. The second orbit carries exactly 2 units. The third carries 3. There is no orbit with 1 and 1/2 units. There is no orbit with pi units. The angular momentum of an electron in orbit is always a whole number, and that whole number multiplied by h-bar gives you the exact angular momentum. This was a radical departure from classical mechanics. It said that angular momentum was not a continuous dial. It was a discrete counter clicking up in whole number steps. Bohr's model worked for hydrogen. It predicted the spectral lines with remarkable accuracy. But it was built on assertions, not derivations. Why could the electron only occupy those specific orbits? Why those exact angular momenta and no others? Bohr did not know. The model was a rule imposed on nature, not an explanation emerging from nature. It would take another decade for the true answer to arrive, and when it did, it would not come from orbits at all. In Frankfurt in 1921, 2 physicists set up one of the most important experiments in the history of quantum mechanics. Otto Stern was the theorist. Walter Gerlach was the experimentalist. Their apparatus was simple in concept and extraordinarily difficult in practice. A beam of silver atoms shot through a region of inhomogeneous magnetic field and collected on a glass plate on the other side. The idea behind the experiment was to test whether the angular momentum of an atom was quantized. Silver atoms have a single electron in their outermost shell, and that electron carries angular momentum. A magnetic field exerts a force on a magnetic dipole, and the direction of that force depends on the orientation of the dipole relative to the field. If angular momentum could point in any direction, the magnetic moments of silver atoms would point in all directions randomly. The magnetic field would then deflect the atoms across a continuous smear on the collection plate, spread from top to bottom in a smooth gradient. If angular momentum could only take on discrete orientations, the beam would split into distinct spots. Think of it like a coin sorting machine that is supposed to sort coins by weight. If you fed it an infinite variety of different weights, it would distribute them smoothly across its output. But if only a few exact weights exist, you get distinct piles with empty space between them. The machine does not create the discreteness. It reveals what was already there. Stern and Gerlach expected two possible results. They expected either a continuous smear confirming the classical picture or perhaps a few discrete spots confirming quantization. They sent silver atoms through the apparatus and collected them on the plate. Two spots, exactly two, no smear, no additional spots above or below. Two discrete locations where silver atoms arrived, separated by a gap where none arrived. Walter Gerlach sent a postcard to Niels Bohr announcing the result. The two physicists had been smoking cheap cigars throughout the experiment, and those cigars left a mark. The sulfur in the cigar smoke deposited silver sulfide on the glass plate, making the pattern visible. The two spots that confirmed quantization were revealed by cigar smoke. The result was clear, but its interpretation would take years to untangle. The silver atoms in the experiment had an outer electron in a particular orbital configuration, and that orbital angular momentum should have predicted three possible orientations producing three spots. The two-spot result did not match orbital angular momentum at all. Something else was contributing. Something with a value that could only orient in exactly two ways. Never three, never five. Not a continuous smear of possibilities that something was not yet named. The theoretical framework to understand it did not yet exist. But the experiment had drawn a line in the ground. The angular momentum of an electron was not a continuous dial pointing in arbitrary directions. It was a discrete quantity. It came in specific amounts and pointed in specific orientations. Everything between those orientations was forbidden. The question the experiment left open was devastating. If this extra angular momentum belonged to the electron itself, and if angular momentum always came from rotation, then the electron had to be rotating. But what could it be rotating about? And what determined the exact amount? Those questions had answers. The answers were stranger than anyone had been prepared for. To understand what the Stern galactic result was actually measuring, you first need to understand that electrons carry two completely separate kinds of angular momentum. Physicists had been treating them as one, which was part of why the two-spot result was so confusing. Untangling them required recognizing that a single electron can be both moving through space in a pattern around the nucleus and simultaneously carrying something internal that behaves like rotation but is not. The orbital angular momentum is the kind Bohr had quantized in his model. It comes from the electron's movement around the nucleus. In the silver atom used in the Stern-Gerlach experiment, the outer electron happened to be in a state with zero orbital angular momentum. It was in the lowest energy orbital configuration, which carries no orbital angular momentum at all. So the two spots could not have come from orbital motion. They came from the second kind, the kind nobody had a name for yet. Consider the Earth. It has two completely separate kinds of angular momentum, and they are entirely independent of each other. The first comes from its orbit around the Sun. Earth moves through space in a vast ellipse, taking 365 days to complete one circuit. That motion carries enormous angular momentum tied to the mass of Earth, the speed of its travel, and the size of its orbit. You cannot change one of those quantities without changing the others. The second comes from Earth spinning on its own axis. Once every 24 hours, the planet rotates about a line running through the poles. That rotation is a separate quantity entirely. If Earth were somehow made to spin faster on its axis, While keeping its orbital speed the same, its orbital angular momentum would be unchanged. The two are coupled to each other only loosely through tidal interactions over very long time scales. For most purposes, they are independent. Electrons have the same two kinds. They have orbital angular momentum, which comes from moving around the nucleus. They also have something else, something intrinsic to the electron itself, regardless of how it is moving or where it is. Physicists named the second kind spin because it resembled the spin of a planet about its own axis, the self-rotation independent of the orbit. In 1925, George Oland Beck and Samuel Gauss-Schmidt were two young physicists working under Paul Ehrenfest at the University of Leiden. They were trying to explain a puzzling pattern in the spectral lines of atoms. When atoms were placed in a magnetic field, their spectral lines split into pairs. An orbital electron, in a specific state which should have produced one spectral line, was producing two. The splitting implied that the electron had an additional source of angular momentum, one that could orient in one of two ways relative to the magnetic field. Oland, Beck, and Gauss-Schmidt proposed that the electron was literally spinning about its own axis, the way Earth spins about its poles. A spinning charge creates a magnetic field. That magnetic field would interact with any external field, and the two possible spin orientations would produce two slightly different energy states, explaining the doubled spectral lines. The proposal fit the experimental data. The amount of angular momentum required to explain the splitting was exactly 1/2 of the fundamental unit har. Not 1 unit like the lowest orbital angular momentum. Not 2, 1/2. This was immediately strange. Orbital angular momentum comes in whole number multiples, 0, 1, 2, 3. Nothing else is permitted. Nothing between. Spin came out as 1, 2. What did it mean for angular momentum to be a half integer? What geometric picture corresponded to that number? Uhlenbeck and Gauss-Schmidt wrote up their proposal and gave it to Ehrenfest to evaluate. He told them it was either very interesting or very wrong and sent it to a journal. Before the paper appeared in print, they showed the calculation to Hrik Lorentz, the elder statesman of Dutch physics. Lorentz ran the numbers. His reply was devastating. If the electron is physically spinning, then to carry 1/2 of h bar of angular momentum, the surface of the electron would have to move at a speed far exceeding the speed of light. The calculation was not approximate. It was not off by a small factor. It required the electron surface to move at roughly 100 times the speed of light, with some estimates putting the required velocity even higher, depending on how the electron's masses were assumed to be distributed. Uhlenbeck and Gauss-Schmidt immediately went to Ehrenfest and asked him to withdraw the paper. He told them it was already in print. He also told them that being young was an advantage. Young physicists could afford to say foolish things without damaging their reputations permanently. Their proposal was published, and it was correct. But the interpretation, the literal spinning electron, was completely and provably wrong. So physicists were in a peculiar position. They had a quantity that behaved exactly like angular momentum. It added to orbital angular momentum in the right way. It interacted with magnetic fields in the right way. It explained the spectral line splitting precisely. But it could not be rotation, because the rotation required would be physically impossible. The electron is either a point with no radius, in which case rotation is meaningless, or it has some radius, in which case the rotation required would demand speeds the universe forbids. The word spin was already attached to the concept. It stayed, but the picture behind the word was gone. What remained was the number 1, 2, and that number was stranger than it first appeared. There is a trick you can do with a belt. Take a belt and clip one end to a fixed point, a doorwork knob, or a hook on a wall. Hold the other end in your hand. Now twist the belt by rotating the hand end 360 one full turn. The belt now has a twist in it. Try to untwist it without rotating the end in your hand and without going around the fixed point. You cannot. The twist is locked in. One full rotation has put the belt into a state that cannot be returned to the original by any combination of movements that do not themselves involve rotation. Now twist it again another 360 in the same direction. Now the belt has been rotated a total of 720 two full turns. Something strange happens. Now you can untwist it completely. You can pass the end of the belt around the twisted section, and the belt returns to its original flat state. Two full rotations is equivalent to no rotations in a way that one full rotation is not. This is not a trick of the belt's flexibility. It is a genuine mathematical property of how certain objects relate to the geometry of three-dimensional space. It is called the Dirac belt trick after Paul Dirac, who used it to illustrate properties of quantum spin, and it reveals something profound about what the number 1-2 means. For ordinary objects, a 360-degree rotation returns everything to its original state. You spin a basketball once, and it looks the same as before you started. You spin a cube once, and the cube is back where it began. For these objects, one full rotation is the same as no rotation. Mathematically, they have what physicists call integer spin. Spin 1 particles are like that. A photon which carries 1 unit of spin, angular momentum, returns to its original quantum mechanical state after 1 full rotation. Spin 2 particles return after half a rotation. Spin 0 particles look the same no matter how you rotate them. But spin 1 and 2 particles are the belt. 1 full rotation does not return them to their original state. The mathematical object that describes a spin 1 to 2 particle changes sign after a 360-degree rotation. It becomes the negative of what it was. Only after a second full rotation, 720 total, does it return to its starting configuration. This sounds like an obscure mathematical technicality. It is not. It has real measurable consequences. In the 1970s, physicists performed experiments with neutron beams in which part of a neutron's wave was passed through a magnetic field that caused it to precess at a controlled rate, effectively rotating the neutron's spin state. When they recombined the two parts of the beam, the interference pattern between them revealed exactly this property. The intensity of the interference oscillated once per 720 degrees, confirming that a 360-degree rotation changed the sign of the neutron's quantum state. The experiment was not a philosophical curiosity. It was a direct measurement of the geometry of spin 1-2. And this geometry has no analog in classical physics. There is no classical object that behaves this way. There is nothing in your ordinary experience that requires 2 full rotations to return to its starting state. The belt trick hints at it, but the belt trick works because of the belt's extension into the surrounding space, which can absorb the twist. The electron has no extension into surrounding space. Its spin is intrinsic. The 720 property is not because of something attached to it. It is the electron itself. The number 1-2 is not just a measurement result. It is a statement about how the electron relates to the geometry of the universe. And nothing with that relationship to geometry can be a classical spinning object. Think about what the half-integer means for the observable quantity. When you measure the spin of an electron along any axis, you never get 0. You never get 1 whole unit. You get +1 to 2 or -1 to 2. Those are the only 2 possible answers. Not approximately those values. Exactly those values every single time with no spread. For a quantity that is supposed to be analogous to angular momentum, this is remarkable. Orbital angular momentum can be 0. An electron in the lowest energy state of hydrogen has 0 orbital angular momentum. But spin is never zero for an electron. It always has exactly 1/1/4 of a unit oriented either in the direction you measured or opposite to it. The electron never has no spin. The electron is never unspun. This raises a question that cuts to the core of what spin actually is. The spin is not zero when the electron is at rest. It cannot be turned down or removed. It exists regardless of the electron's motion or energy state. What kind of physical property behaves like that? What kind of physical quantity is fixed forever, immune to every external influence, and incapable of being absent? Let us do the calculation that Lorentz did, the one that stopped Uhlenbeck and Goudsmit in their tracks. To carry angular momentum, a spinning object needs mass moving at some distance from the center of rotation. The amount of angular momentum is determined by the mass, the speed, and the radius. If you know how much angular momentum you want, and you know the mass, you can calculate what combination of radius and speed is required. Physicists have measured the mass of the electron with precise precision. It is about 9.1 × 10^31 kg. Vanishingly small, but not zero. An electron has mass. They have also measured what is called the classical electron radius, about 2.8 × 10^15 mm. This is not the actual measured physical size of the electron, because the electron appears to be a point particle with no measurable radius. The classical radius is instead derived from a theoretical calculation. It is the radius at which the electrostatic self-energy of a charged sphere would equal the rest mass energy of the electron. It is the largest the electron could plausibly be, while remaining consistent with what we know about it. Think of it as an upper bound, the largest allowed physical size. Now ask the question, if a sphere of this mass and this radius was spinning fast enough to carry 1/2 of a unit of h-bar in angular momentum, how fast would its surface have to move? Imagine a pizza being stretched by a chef. As the pizza spins, its edge moves faster than its center. Spin the pizza faster, and the edge moves faster still. Now, imagine making the pizza smaller while keeping the same total spin. The edge has less distance to travel per revolution. So to maintain the same angular momentum, it has to move even faster. Now make it the size of an electron. Now require it to carry spin 1/2 in angular momentum. The surface velocity required is approximately 100 times the speed of light. Some calculations put it at several hundred times. The exact factor depends on assumptions about how the mass is distributed inside the hypothetical sphere. But no assumption brings it below the speed of light, by even an order of magnitude. The speed of light is not a traffic law that exceptionally fast objects can break with enough energy. It is a logical limit baked into the structure of space-time. Nothing with mass can reach it. Nothing can exceed it. A surface moving at 100 times the speed of light is not a physical object. It is a logical contradiction. And this is true even using the most generous possible assumption about the electron size. If the electron is smaller than the classical radius, the surface has to move even faster. If the electron is a true point particle with no radius at all, then the concept of surface rotation becomes meaningless. A point cannot rotate about itself. Either way, the calculation is fatal. A classical spinning electron simply cannot exist. What Lorentz had discovered in pointing this out to Uhlenbeck and Goudsmit was not a problem with their proposal. It was a signpost. The angular momentum was real. The experimental evidence was solid. The spinning sphere model was the wrong picture. Something else entirely was responsible for the angular momentum of the electron. Something that carried a half-integer value, obeyed the 720-degree rotation rule, and interacted with magnetic fields exactly as spin predicted without requiring anything to actually spin. Physicists had a quantity with no mechanism behind it. That is an uncomfortable position in physics. Quantities are supposed to come from somewhere. They are supposed to be understandable in terms of something moving, something changing, something happening. Spin did not follow that rule, and the explanation for why would have to wait for someone who was willing to start from completely different foundations. The person who found those foundations was not working on the electron spin problem directly. He was working on a different problem entirely: how to make quantum mechanics consistent with special relativity. But the answer to that problem contained spin inside it unavoidably, as if the universe had been hiding it there all along, waiting for someone to write the right equation. Paul Dirac was 26 years old and working in Cambridge in 1928. He had a problem that was bothering him deeply. The Schrödinger equation, which had just been formulated 2 years earlier and which described quantum mechanical particles beautifully, was not compatible with special relativity. It treated time and space differently. At high speeds, close to the speed of light, it gave wrong answers. An equation that described reality well for slow particles but failed for fast ones could not be the final story. Drake was not a physicist who could tolerate incomplete answers. He was famously precise, famously true, famously willing to follow the mathematics wherever it led, even if the destination seemed physically nonsensical. He set out to write a relativistic equation for the electron, an equation that would treat time and space on equal footing, that would reduce to the Schrödinger equation at low speeds, and that would give correct results at any speed up to the speed of light. He succeeded. The Dirac equation, as it is now called, is one of the most beautiful objects in theoretical physics. Written out in full, the Dirac equation is compact and elegant and apparently simple. Its consequences are not. When Dirac solved his equation for a free electron, something fell out that he had not put in. The equation's solutions required the electron to have an internal degree of freedom with exactly 2 possible states, not as an additional assumption, not as an ingredient he added to make it work. The 2-state structure was a necessary consequence of combining quantum mechanics with special relativity. Spin was not a separate property grafted onto the electron to explain the Stern-Gerlach experiment. It was something mathematics demanded. Any particle described by Dirac's relativistic quantum equation necessarily has spin 112. The half-integer angular momentum was not a measurement anomaly requiring explanation. It was unavoidable. Think of a compass needle. The needle always has a north end and a south end. You cannot make it have only one end or no ends or 3 ends. The directional property is intrinsic to what a compass needle is. It does not come from the needle spinning about an axis or moving through space. It comes from the needle being what it is with its particular internal structure. Take away the motion and the property remains. Spin is like that. Deeper than that. In fact, the compass needle's north-south property ultimately comes from the behavior of its atoms, which are themselves quantum objects. Spin exists below that level, at the level of the electron itself, where there is nothing further down to appeal to. The Dirac equation revealed that spin is not a property the electron happens to have. It is a property the electron cannot not have given what the electron is. This was the resolution to Owenbeck and Goodsmith's crisis. Spin is not the electron rotating. Spin is what you must have when you write a quantum mechanical description of a massive charged particle that is consistent with special relativity. The angular momentum is real. The conserved quantity is real. The interaction with magnetic fields is real. But the mechanism is not rotation. The mechanism is the geometry of relativistic quantum field theory. Dirac's equation also predicted something else that seemed absurd at the time: the existence of a positively charged version of the electron. A particle with the same mass and spin as the electron, but opposite charge. Dirac was reluctant to accept this prediction from his own equation, but in 1932, Carl Anderson detected it in cosmic ray tracks, the positron, the first antiparticle. It had been written into the equation before anyone knew it existed. Spin, intrinsic, and irreducible came out of the same equation that predicted antimatter. Both were consequences of combining quantum mechanics and special relativity. Both were there in mathematics before they were confirmed in the laboratory. The electron spin is not something we measured, and then tried to explain. It is something the universe's fundamental symmetries require. But accepting that spin is intrinsic and not rotational leaves an immediate question on the table. If spin is a fixed internal property of the electron, what does it mean to say it can orient in two different ways? If the electron is not rotating, what is it that changes when you go from spin up to spin down? What are those two states? And why exactly two? Suppose you have a coin, not a quantum coin, just an ordinary one. Before you flip it, you might say it has some probability of landing heads and some probability of landing tails. But the coin is actually a definite object. It has a definite orientation sitting in your hand before the flip. You are just uncertain about what the outcome will be. The coin itself is not in a superposition. It is not simultaneously heads and tails. It is one thing and you do not know which until it lands. The electron spin is not like that coin. Before you measure the spin of an electron along a given axis, the electron does not have a definite orientation along that axis. It is genuinely mathematically physically in both states at once, not unknown to you, not hidden behind a curtain. Both the measurements does not reveal what was already there. The measurement forces a result that did not exist as a definite outcome before the measurement occurred. When you choose an axis and measure spin along it, you always get one of exactly two results. Along the vertical axis, you get spin up or spin down relative to vertical. Along the horizontal axis, you get spin up or spin down relative to horizontal. Pick any axis in the universe, and the answer is always one of two values, plus 1 and 2 or minus 1 or 2 in units of h-bar. No partial alignment, no diagonal result, no fractional answer. This binary outcome is not a limitation of your measuring instrument. It is a fundamental feature of the geometry of spin 1 to 2. The magnitude of the spin angular momentum is fixed at a value slightly larger than 1/2 of h-bar because of a quantum mechanical formula involving the square root of s, Friedrider s plus 1c1, where s is 1 to 2. But when you project that spin onto any axis, the component along that axis is always exactly plus or minus 1 to 2. No more, no less. You might ask, if the electron has some definite spin direction before measurement, why do you get a random outcome when you measure along a different axis? The answer is that the electron does not have a definite spin direction before measurement. It has a quantum state which contains probability amplitudes for different outcomes along different axes. Those amplitudes are not expressions of your ignorance. They are the actual state of the electron. The definitesse is created by the measurement, not revealed by it. And here is the part that should make you pause. Once you have measured the spin of an electron along the vertical axis and gotten spin up, you know it spins along that axis. Now tilt your detector 90 degrees and measure again along the horizontal axis. The result is random, 50% probability of each outcome. The previous measurement along the vertical axis gave you definite information about the vertical component, but it destroyed any definite information about the horizontal component. You cannot simultaneously know the spin of an electron along two perpendicular axes. Measuring one erases the other. This is not because the measurement is clumsy or the instrument is imprecise. It is a fundamental consequence of the mathematics of spin 1 to 2. The spin components along different axes do not commute. The order in which you measure them matters. Measuring along one axis changes the state of the electron relative to all perpendicular axes. The electron does not carry pre-existing definite values along all axes simultaneously waiting to be discovered. Those values are created by the act of measurement. The Stern-Gerlach apparatus demonstrated this beautifully. Send silver atoms through a vertical Stern-Gerlach device, and you get two spots spin up and spin down relative to vertical. Take the spin-up atoms and send them through a horizontal Stern-Gerlach device. Two spots again, spin up and spin down relative to horizontal. Take the spin-up horizontal atoms and send them back through a vertical device. Two spots, not one spot. The selection of horizontal spin-up did not preserve the vertical spin-up state. It destroyed it. The two possible orientations of spin are not like the two orientations of a bar magnet sitting in a drawer pointing either north or south depending on which way you put it in. They are the two possible results of a question asked by a physical apparatus, a question whose answer does not exist before the question is asked. This is what quantum angular momentum is, a property that is real, a property that is conserved, a property that influences magnetic fields and determines chemical behavior and shapes matter, and a property that does not take on definite values along any given direction until you ask, and whose definiteness along one direction erases definiteness along all perpendicular directions simultaneously. Here is a result from classical electromagnetism that is as reliable as any in physics. A moving electric charge creates a magnetic field. You have seen this, an electric current in a wire, which is nothing more than electrons drifting along a conductor, creates a magnetic field around the wire. That field is strong enough to deflect a compass needle to lift iron filings to drive an electric motor. The charge in motion and the magnetic field are inseparable. They always appear together. A classical spinning charged object should therefore produce a magnetic field of its own. Take a charged sphere and set it rotating. The charge on its surface is now moving. Moving charge is current. Current produces magnetism. So a spinning charged sphere behaves like a tiny magnet with a north and south pole aligned with its spin axis. The strength of that tiny magnet depends on the charge, the mass, and how the charge is distributed relative to the mass. The electron has charge. The electron has spin. The electron, therefore, has a magnetic moment. It behaves like a tiny bar magnet. The north and south poles of that magnet are aligned with the electron spin axis, and when you place the electron in an external magnetic field, the field exerts a torque on the electron's magnetic moment, the way an external magnetic field exerts a torque on a compass needle trying to align with it. This is exactly what the Stern-Gerlach experiment detected. The inhomogeneous magnetic field in the apparatus exerted different forces on atoms depending on the orientation of the atomic magnetic moment, which in turn depended on the spin orientation of the outer electron. The two spots on the glass plate were not just evidence for discrete spin states. They were evidence for discrete magnetic moment orientations, which is the same thing measured differently. Now here is the strange part. For a classical spinning charged sphere, there is a definite ratio between the magnetic moment it produces and the angular momentum it carries. This ratio is called the gyromagnetic ratio. For a classical sphere with uniform charge and mass distribution, the gyromagnetic ratio has a specific predicted value. When physicists measured the gyromagnetic ratio of the electron, they found it was approximately twice the classical predicted value. The electron produces about twice as much magnetic field per unit of angular momentum as a classical spinning sphere would. This factor of 2 is called the G factor of the electron. Its classical expectation is 1. Its measured value is approximately 2, more precisely about 2.02. The small departure from exactly 2 is a prediction of quantum electronics and one of the most accurately verified results in all of physics. The measured G factor of the electron and the theoretically calculated G factor agree to more than 10 decimal places. This is the most precisely tested prediction in science. But the basic factor of 2 is already telling you something. It is telling you that spin is not the angular momentum of a classical spinning sphere. A classical sphere with the same charge and mass distribution as the electron would give g^1. Spin gives g^2. The relationship between the magnetic moment and the angular momentum is different from anything you would get by rotating a sphere. Think of a gyroscope wobbling on a table. When you push the tip of the gyroscope sideways, instead of tipping over as you would expect, it precesses. The spin axis swings around in a circle perpendicular to the force you applied. This is a gyroscopic precession, and it is a direct consequence of the angular momentum the gyroscope carries. When you push sideways on angular momentum, the angular momentum rotates rather than stops. The electron's spin does the same thing in a magnetic field. A magnetic field exerts a torque on the electron's magnetic moment, and instead of simply aligning with the field, the spin axis precesses around the field direction in a circle. The rate of this precession is called the Lama frequency, and it depends on the strength of the magnetic field and the gyromagnetic ratio of the electron. This precession is not a curiosity. It is the operating principle of magnetic resonance imaging, the MRI machine that hospitals use to produce detailed images of soft tissue inside your body. The hydrogen nuclei in your body's water molecules have their own spin and their own magnetic moments. When you are placed in a strong, precisely tuned magnetic field, those proton spins precess at a specific frequency. A pulse of radio waves at exactly that frequency tips the spins away from alignment. And as they precess back into alignment, they emit a radio signal. The timing and strength of that signal measured from different angles is reconstructed into a three-dimensional image. The image of your brain or your knee on an MRI scan is a picture drawn with quantum spin. Every voxel in that image represents the spin precession of hydrogen nuclei. Every detail in the image reflects the quantum mechanical angular momentum of particles with no classical rotation. Spin is not an abstract theoretical property. It is the thing your doctor looks at. Wolfgang Pauli was one of the most brilliant and most caustic physicists of the 20th century. He had an uncanny ability to identify what was wrong with an argument before the argument was finished, and he was not gentle about saying so. He once described a paper as so bad it was not even wrong. Colleagues quietly dreaded presenting their work to him. In 1925, before Uhlenbeck and Gauss-Schmidt proposed the spinning electron, and before Dirac derived spin from his relativistic equation, Pi was staring at the spectral data of atoms placed in magnetic fields, and he noticed a pattern. Each quantum state of the electron in an atom could be fully described by 4 numbers. 3 of those numbers characterize the orbital behavior, the energy level, the orbital angular momentum, and the orientation of that orbital angular momentum relative to a reference direction. The 4th number was something new, something he called a 2-valuedness, and it could be +1,2 or -1,2. He did not know what it was. He did not care for the moment what it was. What he noticed was this: no 2 electrons in the same atom ever had the same combination of all 4 numbers. He announced this as a rule without derivation and without explanation. Every electron in an atom occupies a unique combination of quantum numbers. No 2 electrons can share all 4 values simultaneously. This became the Pauli Exclusion Principle, and it was one of the most consequential rules in all of chemistry. Think of a hotel where each room has a unique combination of 4 features: the floor number, the room style, the view direction, and a final attribute that comes in only 2 varieties: left-facing or right-facing. Every guest who checks in must go to a room with a unique combination of all four features. No two guests share all four simultaneously. The hotel fills up in a very particular way. One guest per unique combination, two guests per room. If we interpret the last attribute as two subrooms within each room, this is how electrons fill the shells of an atom. The first energy level can hold two electrons, one spin up and one spin down, the only two allowed values of the fourth quantum number. The second energy level can hold 8 electrons distributed across the orbital sublevels and their orientations with 2 electrons per orbital due to the two spin states. The third can hold 18. The pattern is not arbitrary. It follows directly from counting the allowed combinations of quantum numbers with spin contributing a factor of 2 at every level. The periodic table is a direct consequence of this filling. Hydrogen has 1 electron in its first shell, not quite full. Helium has 2, 1 spin up and 1 spin down, completing the shell and making helium chemically inert. Lithium has its third electron forced into the second shell, giving it a loosely held electron that makes it reactive. Neon fills the second shell and is inert again. Every period in the periodic table corresponds to filling a set of orbitals, with spin determining the capacity of each. Remove spin from the Pauli Exclusion Principle, and the periodic table collapses. Without the 2 spin states per orbital, each orbital would hold only 1 electron. The filling patterns would be completely different. The chemical properties of every element would change. The molecules that make up your body would not form. The proteins, the DNA, the lipids in your cell membranes. All of it depends on the specific electron filling patterns of atoms. Those patterns depend on the Pauli Exclusion Principle. The Pauli Exclusion Principle depends on spin. Pauli announced his principle in 1925 without knowing what the two valuedness were. He was criticized for introducing an unexplained quantum number without physical justification. He was right to do it anyway. The pattern in the data was unmistakable, and the correctness of the rule did not depend on understanding its origin. What Pauli had found was the shadow cast by spin across the structure of all matter. The thing he called two-valuedness, the thing he could not explain, was spin. And its refusal to let 2 electrons share a state was about to turn out to be the reason the world is solid. Why can you not push your hand through a table? The obvious answer, the one you carry from childhood, is that atoms are solid. The table is made of wood. Wood is made of molecules. Molecules are made of atoms, and atoms in this familiar picture are solid little balls that block each other. But this answer is wrong. Atoms are almost entirely empty space. If the nucleus of a hydrogen atom were the size of a marble, the electron cloud around it would extend to a sphere about 1 kilometer in diameter. The vast majority of every atom is nothing. The vast majority of your hand is nothing. The vast majority of the table is nothing. So why does your hand stop? The answer is the Pauli Exclusion Principle applied to electrons. When you press your hand against the table, you are bringing the electron clouds of your hands into proximity with the electron clouds of the table's atoms. The electrons in your hand and the electrons in the table are fermions. They obey the Pauli Exclusion Principle. If 2 electrons from different atoms try to occupy the same spatial region in the same quantum state, the exclusion principle prohibits it. Electrons cannot be forced into the same state. The resistance you feel is not the hardness of solid balls colliding. It is a quantum mechanical pressure generated by the refusal of electrons to share quantum states. Physicists call this degeneracy pressure. It is not a force in the conventional sense, not a push generated by one object against another. It is a consequence of the mathematics of quantum states that prevents multiple fermions from occupying the same region in the same configuration. The pressure increases rapidly as you try to compress the electrons closer together, because compressing them into a smaller volume forces them to share more similar momentum states, which the exclusion principle resists. This degeneracy pressure is enormously strong. It is the reason white dwarf stars do not collapse. A white dwarf is what remains after a star like the Sun exhausts its nuclear fuel. The outward pressure of nuclear burning is gone. What prevents the star from collapsing under its own gravity is not heat, not nuclear reactions, but electron degeneracy pressure. The electrons in the white dwarf are packed so densely that the Pauli exclusion principle generates enough outward pressure to balance the inward pull of gravity. A white dwarf the size of Earth can contain a mass comparable to the Sun, held up by nothing but spin. When gravity is strong enough to overcome even electron degeneracy pressure, the electrons and protons are forced together, producing neutrons through inverse beta decay. Neutrons are also fermions with spin 112. They also obey the Pauli exclusion principle. Neutron degeneracy pressure holds up neutron stars, objects typically about 20 kilometers across and carrying 1 and 1.2 times the mass of the Sun. All of that mass, all of that compressed matter, held against further collapse by the refusal of neutrons to share quantum states. And when gravity overcomes even neutron degeneracy pressure, nothing holds up the collapse. The result is a black hole. The solidity of matter on Earth, the stability of white dwarfs, the existence of neutron stars. These are a single line of consequences from one property. The electron has spin 1,2 that makes it a fermion. Fermions obey the Pauli exclusion principle. The exclusion principle generates degeneracy pressure. Degeneracy pressure holds matter apart at human scales and holds dead stars together at cosmic ones. All of that from a number 1 to 2. But the story splits here because not all particles are electrons. Not all particles have half-integer spin. Some particles have integer spin, and they play by entirely different rules. The difference between those two families of particles is the deepest organizational principle in the structure of matter and energy. Think about what you feel when you press your fingertip gently against the surface of this table, or the floor beneath you, or any solid object. That resistance, that firm refusal of the surface to give way, is not the hardness of anything physical pressing back. It is a consequence of the mathematical structure of quantum states applied to a property of particles that is itself not a rotation. The table is holding your hand up using quantum mechanics, and the quantum mechanics it is using is built entirely on spin. The universe divides all its fundamental particles into two families based on a single criterion, whether their spin is a half-integer or a whole number. Electrons have spin 1.2. Quarks have spin 1.2. Protons and neutrons, which are made of quarks, are composite particles, but they also behave as spin 1.2 particles. These are furions named after Enrico Fermi, who, along with Paul Dirac, worked out the statistical rules they follow. Photons have spin 1. The W and Z bosons, which mediate the weak nuclear force, have spin 1. Gluons, which mediate the strong nuclear force, have spin 1. The Higgs boson has spin 0. The hypothetical graviton, if it exists, is predicted to have spin 2. These are bosons named after Satyendranath Bose, who, along with Albert Einstein, worked out the statistical rules they follow. The difference in behavior between these two families is absolutely not a matter of degree. Fermions obey the Pauli exclusion principle. No two identical fermions can occupy the same quantum state simultaneously. They are antisocial. They refuse to crowd. They stack in layers with one per allowed state, filling the available quantum states from the bottom up. The Pauli exclusion principle applies without exception to all of them. Bosons have the opposite tendency. Multiple identical bosons can occupy the same quantum state. Not just can, they are actively encouraged to. The probability of a boson entering a particular state increases with the number of bosons already in that state. Bosons crowd together. They pile into the lowest available state. When many bosons occupy the same quantum state, they form a coherent collective phenomenon that classical physics has no equivalent for. Consider a laser. Inside the laser cavity, photons are being emitted by excited atoms. Each emitted photon is a boson. Photons prefer to enter states that are already occupied. A photon in a given quantum state stimulates the emission of another photon in the same state, which stimulates another, and so on. The result is a cascade. Trillions of photons, all in exactly the same quantum state, marching together with identical wavelength and direction and phase. They are indistinguishable from each other in every quantum mechanical sense. A laser of electrons would be impossible. Try to push two electrons into the same quantum state, and the Pauli Exclusion Principle prohibits it. You cannot stimulate emission in the same way. You cannot build up a coherent beam. Electrons as fermions will not cooperate. The single occupancy elevator versus the freight elevator. A firm elevator admits exactly one passenger per floor and configuration. A boson elevator has no limit, and the more passengers already aboard, the more attractive it becomes. Now cool a collection of bosons to near absolute zero. With very little thermal energy to distribute, all the bosons settle into the lowest available quantum state. Not a few of them, all of them. The entire collection occupies one shared quantum state, losing all individual identity, becoming a single quantum object extended over a macroscopic scale. This is a Bose-Einstein condensate. Bose predicted it in 1924, and Einstein extended the calculation. It was first demonstrated in the laboratory in 1995. The achievement earned a Nobel Prize. The condensate is not a new state of matter in the chemical sense. It is the bosons all becoming the same thing at once. Their individual wave functions merged into one. Superfluidity, superconductivity, the behavior of liquid helium, all of these emerge from bosonic statistics. All of them come from the fact that the particles involved have integer spin. The periodic table comes from fermionic statistics. The laser comes from basic statistics. Two phenomena could hardly be more different in character. Both spring from a single number attached to the spin of a particle. But why does integer spin versus half-integer spin determine these radically different behaviors? The answer to that is one of the deepest theorems in theoretical physics, and it was not fully understood until 1940. And the theorem, when Pauli proved it, linked spin not to particle behavior in isolation, but to how particles behave when you have more than one of them. It linked spin to the mathematics of identity itself. Consider two electrons. They are identical in every measurable sense. Same mass, same charge, same spin magnitude. There is no label on one that distinguishes it from the other. No serial number, no color coding, no property that separates them. Now, swap them. Exchange the positions of electron A and electron B. In classical physics, this changes nothing observable. If two billiard balls are identical, swapping them produces an identical setup. Before the swap and after the swap, the system looks the same. The two configurations are physically equivalent. In quantum mechanics, identical particles are described by a joint wave function, a mathematical object that encodes the probability of finding the particles in various configurations. When you swap two identical particles, you are asking what happens to this wave function. There are only two mathematically consistent possibilities. Either the wave function stays exactly the same after the swap, or it becomes the negative of what it was. Those are the only two options that the mathematics of quantum mechanics allows. If the wave function stays the same, It is called symmetric. Particles with symmetric wave functions under exchange are bosons. If the wave function becomes its own negative, it is called antisymmetric. Particles with antisymmetric wave functions under exchange are fermions. This is not a free choice. The spin statistics theorem, which Pauli proved rigorously in 1940, establishes that this choice is completely determined by the spin. Any particle with integer spin, meaning spin 0 or spin 1 or spin 2, has a symmetric wave function. Any particle with half-integer spin, meaning spin 1 to 2, or spin 3 halves or spin 5 halves, has an antisymmetric wave function. There is no freedom. There is no mixing. The spin value locks the statistics. Why? The proof requires quantum field theory and special relativity together. The argument runs through the mathematical structure of how quantum fields behave under Lorentz transformations. The transformations that relate different reference frames in special relativity for integer spin fields. The mathematics forces symmetric wave functions for half-integer spin fields. It forces anti-symmetric ones. Attempt to assign the wrong statistics to a spin, and you get a theory that violates causality, allows signals to travel faster than light, or produces negative probabilities. The universe does not allow any of those things, so it constrains the statistics by constraining the spin. Now, consider what the antisymmetric wave function means for fermions. If two fermions are in the same quantum state, and you swap them, the state is unchanged. There is nothing to distinguish one arrangement from the other. But the wave function also had to become its own negative when they were swapped. Something that is equal to its own negative can only be zero. The probability of finding two fermions in the same state is exactly zero. That is the Pauli Exclusion Principle derived from the spin statistics theorem. It is not an empirical rule imposed on nature. It is a consequence of combining quantum mechanics with special relativity and demanding that the mathematics remain consistent. Think of a handshake. If you and another person shake hands and then you swap positions relative to each other, the handshake looks the same, a symmetric exchange. Now, think of a handshake where swapping the two participants reverses some essential quality of the grip, so that what was clockwise becomes counterclockwise. That is an anti-symmetric exchange. If both participants had exactly the same grip to begin with, reversing the quality would have to produce both the original and its reverse simultaneously, which means neither exists. The handshake between two identical participants with that kind of anti-symmetric structure is forbidden. Fermions cannot share a state because sharing a state with the anti-symmetric condition is a mathematical impossibility. Bosons can share because the symmetric condition imposes no such restriction. Spin is the number that determines which mathematics applies, and the mathematics once applied determines whether you get a periodic table or a laser, a solid table or a superfluid, matter as we know it, or a universe where none of this exists. The spin statistics theorem connects spin to the deepest level of how particles relate to each other and to the geometry of space-time. It is not the last connection. There is one more, and it may be the most disputing of all. Take two electrons and allow them to interact closely enough that their quantum states become correlated. This happens naturally in atoms. Pairs of electrons in the same orbital share a state in which one has spin up and the other has spin down so that the total spin of the pair is zero. When such a pair is formed, the two electrons are described by a single joint quantum state. They are entangled. Now separate them. Move them apart. One electron travels to one laboratory and the other travels to a different laboratory, perhaps on the opposite side of the world. The joint spin state persists in principle, regardless of distance before any measurement. Neither electron has a definite spin along any axis. The pair together has total spin zero. Now measure the spin of one electron along the vertical axis. You get a result, say spin up. At that same instant, the other electron is no longer in an indefinite spin state. It is spin down along the vertical axis with certainty, not because a signal traveled between them, not because the second electron somehow received information about the first measurement, but because the two electrons were never in separate independent states to begin with. Before the measurement, the spin of neither electron was definite. After the measurement of one, the spin of the other became definite. The correlation between them was not carried by any particle traveling at the speed of light. The correlation was built into the joint quantum state from the beginning. Think of two dice that always sum to 7 wherever they are rolled. You throw yours and get 4. Instantly, you know the other dice shows 3, regardless of where it is. A classical explanation would say the dice were preloaded. The 4 and the 3 were determined before you separated them. You just did not know the values until you looked. Hidden variables, a fixed script. John Bell, a physicist at CERN, realized in 1964 that there was a way to test whether that classical explanation was correct. If those correlations came from pre-assigned hidden values fixed at the time of the electron's creation, they would have to obey certain statistical limits. He derived inequalities that any hidden variable theory must satisfy. Bell test experiments, first performed carefully by Alan Aspect and his colleagues in 1982, and refined many times since, have measured those correlations. The correlations violate Bell's inequalities. The correlations are stronger than any pre-assigned hidden variable could produce. The electrons did not have definite spins before measurement. The measurement made the spins definite. Both spins became definite at once, correlated with each other, with no signal passing between them. This is quantum entanglement in spin. It is not a poetic metaphor. It is a laboratory result verified to very high precision that has no explanation in classical physics. The two dice analogy breaks down precisely because classical dice carry their results with them. Quantum spins do not. What entanglement reveals is that two particles that have interacted can share a single quantum state indefinitely even after they are spatially separated. Measuring the spin of one is not learning something that was already there. It is completing a process that instantaneously defines both outcomes at once in correlated fashion across any distance. This is not faster than communication. You cannot use entanglement to send a message because the outcome of your measurement is random. You get spin up or spin down with 50% probability either way, and you cannot control which your partner at the other laboratory also gets a random result. Only when you compare results afterward through a classical communication channel do you discover that the results were correlated. The no communication theorem prevents any useful signal from traveling via entanglement. But the correlations themselves are real. They arise from spin, from the joint angular momentum state of two particles defined at the moment they interact. That joint state persists in principle indefinitely. Quantum spin is not just a property of isolated particles. It can bind particles together across space in a way that has no parallel in classical mechanics. The implication is uncomfortable. Two particles with correlated spins are in some sense still one system regardless of the distance between them. The spin state of each is not fully defined independently. It is only the joint state that is fully defined. There is a temperature at which all thermal motion stops. Absolute 0 Kelvin, 273.15 degrees C at that temperature. Classical physics says every form of kinetic energy is exhausted. Nothing moves, nothing vibrates. The system reaches its ground state, the lowest energy configuration available to it. For most quantities in physics, absolute zero means absence. At absolute zero, a classical object has no kinetic energy and no thermal angular momentum. The spinning stops. Spin does not stop at absolute zero. Every electron still carries spin 112. Every proton still carries spin 112. The spin cannot be reduced. It cannot be extracted. It cannot be transferred to the environment and radiated away. It is not energy that has been stored in rotation and can be released by slowing the rotation. It is a permanent feature of the particle independent of temperature and motion and every external condition. This is one of the sharpest contrasts between spin and classical rotation. A spinning top can always be slowed by friction. Given enough time, every classical spinning object will slow and stop. Friction and air resistance bleed the angular momentum away. Angular momentum will drain away into the environment, distributed across a vast number of molecular interactions averaged into imperceptible warmth. The rotation is temporary. It came from somewhere, and it will go somewhere. Spin has no such history and no such destination. The electron did not acquire its spin when it was created in some particular event and subsequently accumulated it from the environment. The spin is not stored in any structure that can be dismantled. It does not depend on any supporting condition. Take the most depleted, coldest, least active electron in the universe. Its spin is exactly what it is for every other electron. 1/2 of a unit of angular momentum oriented in one of two possible directions when measured and not defined until the measurement occurs. Pauli noticed a consequence of this when he developed the exclusion principle. In an atom at absolute zero, all electrons fill the lowest available energy states in order. Because spin gives each orbital 2 slots rather than 1, and because the exclusion principle prevents any slot from being doubly occupied, the electrons stack into a definite configuration. They do not pile into the lowest single state, the way bosons would. They fill upward, 1 per state, until all electrons are placed. Even at absolute zero, the topmost filled state in a large atom or a metal carries substantial energy because the exclusion principle has forced electrons into high-energy states, even though no thermal energy was available. This is called the Fermi energy, and it is the direct consequence of spin and exclusion applied to a collection of fermions. The Fermi energy is why metals conduct electricity even at very low temperatures. The electrons near the top of the filled states are energetic enough to move when a small electric field is applied. The electrons lowered down are too deep in the stack to participate without an enormous input of energy to lift them over all the ones above them. The conductivity of metals at low temperature. The properties of semiconductors that make transistors possible. The behavior of electrons in a superconductor as they form pairs that circumvent the exclusion principle. All of it traces back to spin, and the ineradicable nature of spin, Andriti 122. Spin is not painted on. It is not a condition that can be modified by finding the right environment or applying the right force. It is woven into the mathematical identity of the particle. The Dirac equation does not describe an electron and then adds spin as an extra feature. The Dirac equation describes a mathematical object that necessarily has spin, and the electron is an instance of that object. Remove the spin, and you do not have a slower, simpler electron. You have something that is not an electron. This is what makes quantum angular momentum different from classical angular momentum in the deepest possible way. Classical angular momentum is a quantity that objects have because of what they are doing. Spin is a quantity that particles have because of what they are. The distinction is total, and it is the distinction that makes the universe what it is. What does it mean for a property to be woven into identity? Consider mass. The electron has a mass of about 9.1 × 10^31 kiloliters. This mass does not come from the electron spinning or moving or existing in a particular field. It comes from the electron's interaction with the Higgs field, a quantum field that permeates all of space. When temperatures in the early universe were high enough, the Higgs field had not yet settled into its current configuration. The particles we now call electrons were massless. As the universe cooled and the Higgs field settled, the electron acquired mass. Mass is something the electron received from its relationship with another field. Charge is intrinsic, in a deeper sense. The electron has a charge of approximately 1.6, 10, 19. This charge is not a consequence of any field the electron is passing through. It is a fixed quantum number, a label attached to the electron at the level of the quantum field theory that describes it unchanged by any process that leaves the particle an electron. You can change the electron's energy, its momentum, its spin direction relative to a measuring device. You cannot change its charge without turning it into a different particle. Spin is like a charge in this respect, but with an extra twist. The electron's spin magnitude 1,2 is fixed by the same mathematics that fixes the charge. The Dirac equation that describes the electron field requires it. Any quantum field theory consistent with special relativity that describes a particle with the charge and mass of an electron also requires it to have spin 1,2. The spin is not separable from the identity of the particle. It is part of what the word electron means. Every particle in the Standard Model has a fixed definite spin that is part of its definition. Photons are always spin 1. Higgs bosons are always spin 0. Up quarks are always spin 1 to 2. These are not measured properties that might vary from one photon or one quark to another. They are features of the quantum field that produces those particles. The field has a definite transformation behavior under rotations in spacetime, and that transformation behavior determines the spin of any particle created from it. The spin is encoded in the symmetries of spacetime itself. Physicists classify particles by how they transform under the group of symmetries that includes rotations and Lorentz boosts. The mathematical group is called the Pankar group. The representations of this group correspond precisely to the possible spin values. Spin 0, spin 1, 2, spin 1, spin 3 halves, spin 2, and so on. Each representation is a different way a quantum field can transform consistently under those symmetries. A particle with spin 1, 2 is a particle that transforms under the simplest, non-trivial spin or representation of the Pankara group. It is a statement not about any motion the particle is performing, but about how the particle relates to the fabric of spacetime. This is the answer to the question that the Stern-Gerlach experiment opened. The experiment showed that electrons have a discrete two-valued angular momentum. Olandbeck and Goldsmith tried to explain it as rotation. Lorentz showed that explanation was impossible. Dirac showed that a fully relativistic quantum mechanical description of any massive charge particle with the electron's properties necessarily produces an object with spin 1,2. The spin is not a property of how the electron moves. It is a property of what kind of mathematical object the electron is, and that mathematical object is determined by spacetime, by the rotational geometry of the universe, by the symmetries that the laws of physics obey. Spin is the electron's relationship to the structure of space and time. Think about that. Every electron in the universe has spin 1,2.12 in every atom on every planet throughout all of cosmic time. 1 to 2, not because electrons were manufactured to have that property, not because some force imposed it, but because any object consistent with the laws of physics that has the electron's charge and mass, and that transforms correctly under the symmetries of spacetime necessarily has spin 1,2. The spin is what the universe is forced to give it by the geometry of existence. You are made of particles that carry a direct imprint of spacetime symmetries. Come back to the spinning top, watch it spin. You can see the motion. You can slow it with your hand. Given enough time and friction, it will stop. The angular momentum drains away. The spinning thing becomes a still thing. Now think about what you are made of. Every atom in your body contains electrons. Each of those electrons carries spin 1 to 2. The spin is not rotating. It is not consuming energy to maintain itself. It is not a motion that could be arrested or a property that could be tuned down. It is there the way the electron's charge is there and the way the electron's mass is there, a permanent feature of the particle's identity, unchanged since the electron was created and unchanged for as long as the electron exists. The electrons in the atoms of your hand are keeping your hand from passing through the table right now. The resistance you feel is not a conventional force between atoms. It comes from the mathematics of antisymmetric wave functions written into physics by the spin statistics theorem, which makes it impossible for those electrons to enter the same quantum states as the electrons in the table. The Pauli Exclusion Principle, which follows from spin, is the mechanism that makes solid matter solid. The hydrogen atoms in the water in your blood were created in the first few minutes of the universe's existence. Their protons carry spin 1 to 2. Over nearly 14 billion years, their spins have been correlated with magnetic fields and entangled with other particles and measured by interactions and returned to superb position countless trillions of times. The spin has not diminished. It has not accumulated or faded. Every proton in your blood carries exactly the spin it was born with. The iron in your hemoglobin is magnetic because of unpaired electron spins. Each iron atom has electrons with spins that do not cancel, leaving a net magnetic moment. That magnetic moment is what makes hemoglobin able to carry oxygen, which is itself attracted to the iron by an interaction that depends on the electron spin states. You breathe because of quantum angular momentum. The light reaching your eyes right now consists of photons. Each photon carries a spin 1. The polarization of light, the property that polarized sunglasses exploit, is a manifestation of photon spin. The color of the light is determined by its energy, but the way it interacts with matter, including the molecules in your retina, depends on the spin states of the photons and the electrons in those molecules. You see, because of quantum angular momentum, the universe you are sitting inside is built from two families of particles. One family carries half-integer spin and refuses to share quantum states. That refusal is why matter is stable, and why atoms have structure, and why the periodic table has the shape it does, and why you are made of distinct atoms rather than one undifferentiated quantum soup. The other family carries integer spin and crowds together. That crowding is why forces can propagate, why light exists, why the electromagnetic field can carry energy across the vacuum of space. The top will spin down tonight. Its angular momentum will scatter into the surface beneath it, into the air around it, into 1,000 imperceptible vibrations. The spinning stops, but the spin in the atoms of the table, in the atoms of the top itself, in the atoms of the air, it pushes against as it slows. That spin does not stop. It was there before the top was made. It will be there after the top has worn to nothing. It is there in every particle in the observable universe, as permanent as the particle itself, as fundamental as the geometry of the space the particle lives in. You've been asking what quantum angular momentum is. Now you know it is not a motion, it is a relationship. It is a particle's relationship to the symmetries of spacetime carried as a fixed number and expressed as a binary choice each time you ask about its direction shaping everything that follows. The spinning top is just the surface. This is what is underneath.